Welcome to our practice test for Chapter 7, AP Calculus. Let's get started. Evaluate the following integrals analytically. Verify your solutions using FNNs. You'll have access to FNN. I'm going to leave that to you. And we've got some pretty easy ones for starters here, so we should be able to get off to a really good start. Integral 2x, that's 2 times x squared on 2. Check the derivative. Yep. We get 2 times x squared on 2. That's going to get us there. So this is just x squared. We get minus x. This would be minus x and plus c. So we've got that. However, this is a defined integral, so we're not going to be dealing with the plus c now. We're now integrating this from negative 3 through 5. So we end up with 5 squared minus 5 minus negative 3, all of it squared minus negative 3, for 25 minus 5, 20, minus 9 plus 3, 12, or a final answer of 8. Okay, this problem, we may be better served by thinking of this as integral 0 to 1, u to the 1/2, u to the first, plus u to the 2/3 du, and distributing this. Integral 0 to 1, u to the 3/2, plus u to the 1/2, that's 3/6, plus 2/3, that's 4/6, u to the 7/6 du. So we get u to the 5/2 on 5/2, or times 2/5, plus u to the 13/6 on 13/6, or times 6/13 from 0 to 1. So we end up with, mercifully, 1 and 0, nice values to deal with. I end up with 2/5 times 1 plus 6/13 times 1 minus 0, 0, big 0. So I get on 65. You can go to calculator on this one, but on 65 times 13, 26 times 5, 30. We end up with 56/65. Okay, and again, you're going to be able to use FNN, but your work is definitely going to support. If I just see an answer of 56/65 and the work doesn't support that, no credit. Okay, antiderivative of secant squared. This is a gift. Antiderivative of secant squared is tangent of theta. We're integrating from pi on 6 to pi on 3. Maybe you need to draw these. Here's pi on 3, root 3 to 1 to 2, and here's pi on 6, 30 degrees, 1 root 3 and 2. So pi on 3 would be root 3 to 1. Pi on 6 minus would be 1 on root 3. How do we want to do this? Let's rationalize. Root 3 minus root 3 on 3, common denominators. Root 3, 3 root 3's minus a root 3 is 2 root 3's on 3. And that is it. So that's first page. Should be able to get through that. If it's similar, which we all know it will be, should be able to get through that pretty quickly. Evaluate the following integrals analytically. Continue to verify. This one we can split into 2 fractions. Maybe you want to try a u du there, but don't have to. This is t to the 3rd on t squared, which is just t, minus 1 on t squared, which I'm going to write as t to the negative 2nd dt. Simple integration here. T to the 2nd on 2 minus t to the negative 1st on negative 1. And maybe I'm taking a step you didn't need to take there, but I'm going to just make this integral t to the 2nd on 2 plus t to the negative 1st dt, and we can just integrate that step by step. So this wants to be t to the third on 3, but it's already on 2, so t to the third on 6. Let's check it. That would be 3t squared. Yep, t squared on 2. T to the negative first. Well, that one's an interesting one, because that wants to be t to the 0th on 0. Oh yeah, that's just 1 on t plus ln t from 1 to 2. So we get 2 to the third on 6 plus ln 2 minus 1 to the third on 6 plus ln 1, or 8/6 4/3 plus ln 2 minus 1/6. The exponent that turns e into 1 is 0, so this is 8/6 minus 1/6, 7/6 plus ln 2. All right. How about this guy? This one, can't split this. However, if I notice the derivative of x squared minus x is 2x minus 1, this should be a pretty simple u du. U is x squared minus x. Du is 2x minus 1 dx. So this is integral 2 to 3 of 1 on u squared. And du actually takes care of everything else. So if I want to think of that as 2 to 3 u to the negative second du, we get u to the negative first on negative 1 from 2. Oh, this was bad. I'm sorry. We're going to be changing these guys for this. I was thinking that this was indefinite, but we need to change these bounds, right? So I put 2 in here, and I get 4 minus 2. This is still 2, but I put 3 in here, and I get 9 minus 3. This is now 6, so it's 2 to 6. Let's double check that. Put 2 in here, and I get 4 minus 2. Got it. Put 3 in here, and I get 9 minus 3. Got it. So this is 2 to 6, or this is negative 1 on u from 2 to 6. So I get negative 1/6 minus negative 1/2, or negative 1/6 plus 3/6, 2/6, 1/3. Okay, we've talked about this a lot. If we got a sine up top, cosine in the bottom, or vice versa, a really good bet is to let u be the trig function in the denominator. So if u is cosine theta, du is negative sine theta d theta. What do I like? Love the sine, love the d theta, don't like the negative. So maybe negative du is sine of theta d theta. So we are going, not going to put my bounds on this time. I'm going to put cosine is in the denominator, so this would be u to the negative 1/2. And then negative du takes care of the rest, so I'm going to go negative and du. So I'm going to put pi on 3 into cosine. You might need to draw the pi on 3. Pi on 3 into cosine. Here's a 1, here's a 2. Cosine is 1/2. So this is 1/2. Cosine of 0, we all know is 1 because the graph of cosine starts up here at 1. So this is 1 to negative 1 to 1/2. You could actually, if you wanted to, make this positive and switch those now. You might not think of that, so I'm going to leave it the way it is. So we get the opposite of 1 to 1/2. Hang on, let's integrate. We get the opposite of u to the 1/2 on 1/2, but on 1/2 is negative 2 u to the 1/2, and we're integrating from 1 to 1/2. Put in 1/2 first, and I get negative 2 times, let's do it this way. I'll just write it this way. 1/2 to the 1/2, or square root of 1/2. And I get minus negative 2 times square root of 1. So plus positive, I get negative 2 on root 2 plus 2. And if we rationalize, let's go ahead and do that. I get negative 2 root 2 on 2 plus 4 on 2, or I get, I'm going to get some reducing here, running out of room. I get 4 minus 2 root 2 on 2, or 2 minus root 2. Okay, let's continue on. Now we've got some undefined integrals. So may want to look at this as 2 minus 3y to the 1/3 dy. At that point, I think I'm going to have u be 2 minus 3y, and then du would be negative 3 dy. I'm not crazy about the negative 3, so all I want is the dy is negative 1/3 du. So what do we have here? We have integral. In place of 2 minus 3y, I've got u to the 1/3. And if I put in a negative 1/3 du, I can pull the negative 1/3 out. Du giving me an answer of negative 1/3 u to the 4/3 on 4/3, but that's times 3/4 plus c, or negative 1/4 u is 2 minus 3y times 2 minus 3y plus c. You want to distribute that? 2 minus 3y to the 4/3. Can't distribute it now. Alrighty. Well, I got choices here. U's going to be sine or u's going to be cosine. I think I like u as sine. Du is cosine of x dx. That couldn't be any better. So we have integral u, plain old du, no accounting for it. U to the 5th, excuse me, du, no accounting for it. So we get u to the 6th on 6 plus c, but that is just sine to the 6x on 6, sine to the 6x on 6 plus c. Okay, choices for u. U could be t cubed. I get a 3t squared du, not very helpful. U could be 1 minus t to the 4th. Du is negative 4. Not crazy about that, but t to the 3rd dt, love that. So t to the 3rd dt may be replaced with negative 1/4 du, and I get integral sine of u, negative 1/4 du takes care of the other parts. So that is negative 1/4 times cosine of u, but the derivative of cosine is negative sine, so I need the opposite of that, plus c, for final answer of positive cosine of 1 minus t to the 4th on 4 plus c. Okay. We should be pretty efficient at these problems. Evaluate the following. How can I do here? Now, this one actually, this is one of the more challenging ones on here. This one's not in a set that says by parts, and there is that really super sneaky way to do this one, but I think I'm going to do this by parts. I think maybe I'm going to call u 2x, and let's call dv, let's see how this works for us. Let's call dv x plus 1 to the 1/2 dx. So I'm going to do this by parts, u dv substitution. I always set it up this way. So u prime, or du, I should say, is 2 dx is just 2. So that's good. And v is the integral of this, which needs to be x plus 1 to the 3/2 over 3/2 2/3. And let's see where we go from there. So our first step in integration by parts, I multiply these, and I get 4/3 x times x plus 1 to the 3/2. And then I've got minus the integral of the product of these, which is 4/3 x plus 1 to the 3/2 dx. All right, well, we can manage that. 4/3 x times x plus 1 to the 3/2 minus 4/3 times integral of this is going to be, wants to be x plus 1 to the 5/2 over 5/2, but that's times 2/5 plus c. So 4/3 x plus 1 to the 3/2, anything reduce, minus 8/15 x plus 1 to the 5/2 plus c. So a little more going on with that one than really any of the others until we get to our by parts. Again, there's a really sneaky way on Slater, I saw it, and I think I prefer this because it's just nice to be able to work with general processes, but you're welcome to take a look at that. Okay, number 11. I will see people from time to time try to split this into x on x squared plus x on 1. Of course, we cannot do that. If this was x squared plus 1 on x, we could split it. So I like u as x squared plus 1 du is 2x dx. What do I need? I just need an x dx, so maybe we want to do this step. I like this step. 1/2 du. So we've got integral 1 on u times 1/2 du takes care of the rest. 1/2 du. So that is 1/2 ln x squared plus 1 plus c. Okay, this looks like a UDV at first glimpse, but then when I notice the derivative of x to the 5th plus 3x is right here. U is x to the 5th plus 3x. du is 5x to the 4th plus 3, and that is just perfect. Integral u to the 1/2 square root of dx. Well, how about that? That is u to the 3/2 on 3/2 or times 2/3. How many times do we do that now? Plus c, or 2/3 times x to the 5th plus 3x to the 3/2 plus c. All right, 18 minutes in and through with the first 12 problems. Use integration by parts. Okay, this is actually a tab process that we could do. I'm going to go through the integration by parts though. If I have a polynomial term like x or x cubed, I'm tempted to have it be u, provided I can take the integral of this easily enough, but I can. So this is u is x, dv is e to the 2x dx, making du 1 dx, making v e to the 2x, but the derivative of e to the 2x is e to the 2x times 2, so we need to be on 2 here. So what do? We multiply those. I get x e to the 2x on 2 minus the product of these, 1/2, or the integral of the product of those, 1/2 e to the 2x dx, or x e to the 2x on 2 minus 1/2 times, what's the integral of e to the 2x? We already got it. E to the 2x on 2 plus c, for x e to the 2x on 2 minus e to the 2x on 4 plus c. Might be tempted to factor out a 1/4 e to the 2x, but that's a good answer right there. Use the tabular method for this. Love it. Here's what I'm going to use for u. I'm going to use x cubed. That's not a fraction there. Just do this. Here's what I'm going to use for dv. is sine of x. I'm not going to put the dx with it for tabular method. So we derivate this down to 0. We integrate this. The integral of sine wants to be cosine, but the derivative of cosine is negative sine. The integral of cosine wants to be sine. The derivative of negative sine, I always check backwards. Derivative of negative sine is negative cosine. The integral of sine wants to be cosine. Well, the derivative of cosine is negative sine. And the integral of cosine wants to be sine, and the derivative of sine is cosine. So we got it. We need this, 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 this. We got a lot going on here. Positive version of this, negative version of this, positive of this, negative of this. I don't think I would want to do this without tabular method. So we end up with negative x cubed cosine of x minus negative plus 3x squared sine of x. All positives plus 6x cosine of x. Just negatives minus 6 sine of x, don't forget it, plus c. Boy, that is slick. Integrate by parts. This is what I'm now referring to as a come-around problem. We've seen a number of these. Let's go ahead and go through this. Both of these, I think we could go either way on this. I'm going to have u be e to the negative x. dv is going to be sine of x dx, making du negative e to the negative x, making v be negative cosine of x. The integral of the derivative of negative cosine is the opposite of negative sine, so we got it. So now I set this up, and I'm going to write small, because I recognize this problem, as you should by this time, as one of these come-around problems. So first step, product of uv, that is negative e to the negative x cosine of x. Second, minus the integral of that. Okay, so that is minus negative, that is a positive, e to the negative x cosine of x, and of course I forgot my dx right here, dx. Okay, so we haven't come around yet, but we're getting closer, I think. So what do we do here? We go, how about u is e to the negative x, dv is cosine of x dx, making du negative e to the negative x dx, making vb wants to be sine of x. Sine's derivative is cosine, so we're in good shape there. So we end up with negative e to the negative x cosine of x is just waiting around. This becomes the product of these, e to the negative x sine of x minus the integral of these, and that's just a single negative, so I'm going to make this positive, e to the negative x sine of x dx, and we have come around. So right now that is equal to the integral of e to the negative x sine of x dx. That's equal to what we're looking for. And I notice here I have a minus the same thing, so I'm going to add that to the other side. Negative e to the negative x cosine of x. I'm going to keep minus e to the negative x sine of x, but because this is a minus an apple, and I've got an apple over here, I'm going to add an apple to both sides, equals 2 times integral e to the negative x sine of 2x dx, or final answer, integral e to the x sine of 2x dx equals negative e to the negative x cosine x minus, where are we at here, minus e to the negative x sine of 2x, all divided by 2 and all plus c. And that's pretty good, but boy, that one is really tempted to, I'm really tempted to take out the 1/2 and take out a negative e to the negative x. So I'm going to go equals negative e to the negative x on 2 times cosine of x plus sine of, where did my 2x come from here? I have no idea where that 2x came from. Sorry about that. Sine of just plain old x. Glad I caught it. So best answer. Okay, I'm going to pause this, and we will come back and talk about more of the practice test. We have a few initial value problems that we're dealing with, and a couple of word type problems, including on your handout. We don't have graphs for this yet, so we will come back on that, and good luck. Took 25 minutes to get there. I would think in a class period, class could get through that portion in 50 minutes time.